Modern integrated air defense systems are engineering marvels designed to track and destroy supersonic fighters and high-altitude ballistic missiles. But these billion-dollar grids have a physical limitation. When targets fly just above the tree line in overwhelming numbers, radar detection geometry breaks down. The system exploiting this limitation on a global scale is the Iranian-designed Shahed-136, rebranded in Russian service as the Garan-2. Headlines frequently label it a suicide drone. That term obscures its actual function. The Shahed is technically a one-way attack unmanned aerial vehicle. In practice, it operates as a precision-guided, low-cost cruise missile. It flies along pre-programmed coordinates and detonates its payload on impact. This chart visualizes the true threat of the platform, the cost-exchange ratio. A single Shahed-136 costs roughly $30,000 to manufacture. The standard surface-to-air interceptor missiles required to shoot it down often cost over $2 million each. This price disparity enables an operational doctrine known as precise mass. By launching dozens of these expendable munitions simultaneously, an attacking force forces the defender to exhaust a finite stockpile of high-end interceptors. Once the air defense grade is saturated and interceptors are depleted, the remaining munitions strike critical energy grids and civilian infrastructure with GPS-guided accuracy. Defeating modern air defenses is no longer strictly a problem of advanced aerospace engineering. The Shahed reduces the airspace to a math equation, where the victor is determined by attrition economics. This 3D wireframe models the Shahed-136, utilizing a cropped delta wing with wingtip stabilizers. This geometry maximizes internal volume. Unlike a traditional fuselage, the blended delta wing provides capacity to house large fuel tanks and a 50-kilogram warhead, generating lift for sustained low-speed flight. Instead of expensive aluminum, the skin is constructed primarily from fiberglass and carbon fiber. This schematic reveals the core beneath the skin, a hexagonal honeycomb lattice. It provides extreme rigidity while keeping the airframe light. Crucially, it provides an electromagnetic advantage. Incoming radar waves penetrate to fiberglass and scatter within the hollow cavities, rather than reflecting back. This scattering effect drastically reduces the drone's radar cross-section. To long-range early warning radars, the 50-kilogram weapon appears no larger than a small bird, allowing it to slip past detection cordons. Debris recovered from combat zones directly confirms this manufacturing technique. The exposed cross-sections of downed Duran-2 airframes consistently show this exact composite honeycomb layout. By utilizing cheap, commercially available materials in a specific geometric pattern, the engineers achieved a pseudo-stealth capability without the need for complex radar-absorbing coatings. The rear of the airframe houses the propulsion system, which reveals an entirely different approach to military procurement. This compares the power plants of the Shahed family. The smaller Shahed-131 relies on the Surratt-1 Wankel rotary engine, generating 38 horsepower. The evolutionary leap to the Shahed-136 utilizes the Mado MD-550, a 50-horsepower, four-cylinder piston engine driving a two-bladed pusher propeller. Neither are proprietary military designs. They are reverse-engineered civilian copies, built for large-model aircraft. Relying on engines designed for the hobbyist market is a deliberate choice. Traded globally with minimal export restrictions, they shield production lines from military sanctions. This geometric scaling from the 131 to the 136 increases wingspan to 2.5 meters, scaling launch mass by 1.5 to 1. The delta wing shape yields 50% more internal fuel volume, extending the Shahed-136's operational range out to 2,500 kilometers. Through basic geometric scaling and unregulated commercial engines, a short-range tactical harassment tool became a strategic deep-strike weapon. The physical airframe and engine deliver the weapon to the target area, but the internal avionics dictate its precision. The guidance system utilizes a dual navigation architecture. It relies on global navigation satellite systems to hit exact coordinates, backed up by an inertial navigation system to maintain heading if the signal is jammed. Yet an analysis of recovered flight control units reveals a paradox. The components driving this system are overwhelmingly manufactured by Western commercial electronics firms. Teardowns consistently identify dual-use commercial hardware, from voltage converters produced by Texas Instruments to radio frequency modules from analog devices. Recent battlefield adaptations integrate standard 4G modems and satellite SIM cards into the control boards, granting operators the ability to update target coordinates mid-flight. Because these microchips and modems are ubiquitous in civilian consumer electronics, tracking and blocking their export through targeted military embargoes is exceptionally difficult. The intelligence guiding the Shahed relies entirely on the unregulated efficiency and accessibility of the global commercial supply chain. Despite its effectiveness, the Shahed-136 has a distinct vulnerability. Its slow cruising speed of 185 km per hour makes it susceptible to basic ground fire. The evolutionary response to that vulnerability is the Shahed-238, designated in Russia as the Garin-3. The core engineering change is a direct swap of the propulsion system. The 4-cylinder piston engine is replaced with a micro-turbojet. This graphs approach speed against time to target. The turbojet pushes the airframe to speeds exceeding 500 km per hour. Tactically, this severely compresses the reaction window. The physical envelope where an interceptor missile can successfully lock on and engage shrinks drastically. However, physics demands a trade-off. The turbojet consumes fuel at a vastly higher rate than a piston engine, meaning the Shahed-238 sacrifices a significant portion of its maximum range to achieve that speed. To compensate, new variants are equipped with active seekers, including electro-optical cameras and anti-radiation sensors. By trading strategic range for tactical penetrability, the platform evolved from a blind coordinate-striking cruise missile into an active hunter-killer. In practice, these variants are not deployed in isolation. They are utilized together in a doctrine known as a Mosaic Defense, operating as a swarm. Attackers deliberately mix slow, piston-driven drones with high-speed jet variants in the exact same wave. This forces air defense tracking algorithms to split their focus, desynchronizing the engagement cycles of the missile batteries. It reduces combat to a mathematical certainty. If the number of incoming cheap drones exceeds the number of ready interceptors in the launch tubes, penetration of the airspace is guaranteed. This overwhelming volume forces a rapid evolution in air defense countermeasures, shifting reliance away from expensive, finite missile stockpiles. Defenders are deploying autonomous, AI-enabled gun turrets designed for rapid kinetic interception. These systems use machine learning to calculate fire control loops instantly, shooting down drones with bursts of low-cost ammunition. Simultaneously, the battlefield has seen the emergence of hunter interceptor drones. These are highly agile, locally manufactured systems engineered specifically to chase down and physically ram jet-powered Shaheds mid-flight. Modern combat is now a collision of two engineering philosophies: exquisite, low-volume legacy systems defending against cheap, mass-produced autonomy. The Shahed family proves that controlling the skies no longer depends solely on superior airframes. It depends on supply chain economics and algorithmic efficiency.